What I'll be talking about tonight is volcanoes, and in particular the sounds from volcanoes. And that's kind of what drew me up here. I think it was a good reason to come up here. It's really interesting research for me. So the title of my talk is Noisy Volcanoes, Jets, Explosion, and Tremor. What I'll be talking about is the different type of volcanic eruptions and the different sounds that they produce. And I've kind of classified them into three general types of sounds. And that's the kind of the jetting, explosions, and then tremor. So that's where that comes from. This is always kind of a neat photograph, I thought, of a Cleveland volcano in the Aleutian Islands. It was taken by an astronaut aboard the space station. And they actually observed this eruption and called down to notify that something was going on, which is pretty remarkable. It also shows some of the motivation for this work. So you can see an ash cloud going up into the atmosphere. And this is obviously a hazard if you were going to flying a plane nearby. So first of all, infrasound is what is the majority of the type of sound produced by volcanoes. So there's different types of sound, and this is what I'll be talking about the majority today. So, but what exactly is infrasound? Well, simply it's just a sound wave at very low frequency. So we all know what a sound wave is, or we can all hear it. But infrasound is essentially all the sound below what humans can hear. Most people can hear between about 20 hertz and 20,000 hertz. And all the sound below what we can hear is just termed infrasound. It's very similar to like a P wave in seismology that propagates through the Earth, except it's traveling through the atmosphere. So everything that I'm talking about, it's going through the air. One of the really kind of unique and interesting things about it is that there's a low amount of energy loss, and so it's able to propagate really long distances. And we're familiar with this if you hear someone with like a big bass speaker. It's able to travel a long distance away, and you can hear these types of things. It's the same with infrasound. We can record sounds from thousands of miles away. I think what's particularly relevant for volcanoes as well is it's not affected by clouds. So just because we can't see what's going on, the infrasound will still propagate away, and we're still able to record it. But we do have to be concerned with the wind and the temperature in the atmosphere, and I'll talk about that more later. This little graphic here is demonstrating all the different types, or some of the types at least, of infrasound, because there are many, or I guess different sources, not types. One that a lot of people are familiar with, about a year ago, the Chelyabinsk meteor came down in Russia and produced a lot of infrasound recorded all over the globe. We picked it up well here in Fairbanks as well. Some other natural sources, the aurora produces sound, infrasound that we record and study here at the GI. The ocean, there's numerous ways it can produce infrasound. These things called microbarometers, crashing surf also does. Severe storms such as tornadoes produce infrasound. Earthquakes, under the right conditions, can produce sound in addition to the seismic waves. Avalanches, which we often get here in Alaska, produce infrasound as well. Chemical and nuclear explosions are also a prime source of infrasound and some of the most well-studied and a lot of motivation and funding for this work. But what I'm most interested in, what I'll be talking about today, is volcanoes in general. So some of the motivation for why we do this and why we study volcanoes and why I study them here. One, monitoring and really understanding volcanoes in Alaska is challenging. And this is for a number of reasons. One is our volcanoes are hard to get to. Most of them are out in the Aleutians. It's difficult to even fly there or get there on a boat, whatever. There's often very bad weather, so we can't see what's going on. And the traditional methods of how we'd monitor these. Also, we have variable activity. It's difficult to predict what's going on at these volcanoes. But one of the things that we try to take advantage of, and what I do, is that these erupting volcanoes, like this one I'm showing here, this is Sakurajima volcano in Japan, produce a lot of sound every time that they erupt. And so that's what we want to do, and what I'll be talking about today. So this is sped up 40 times and playing in a loop. So the top is just the time-lapse imagery, and the bottom is the infrasound data. And this is just pressure that we're recording. And you can see that when it's not erupting, there's no sound coming out, there's no pressure. And then when there's this little explosion, little in quotes, then we get this little pulse right here. And that's I'll be talking about in more detail. So we take this infrasound that we record and we try to understand what's going on at the volcano. And we can do a number of things. We try to determine which volcano is erupting, when does it start, when does it end, how does it change, and what's coming out of the volcano. So just a little bit of terminology without getting into it too much is what's an explosion. Similar to what we would think of from a chemical or nuclear explosion, this is, at least acoustically, a short duration event characterized by rapid volume expansion into the atmosphere followed by a decompression. So we have a lot of pressure built up in the volcano, and we have this really quick release of pressure, and that's what's creating what you just saw in that video. Tremor is something a fair bit different, where rather than being short duration, it's more continuous. It can last anywhere from seconds to years, even. Jet noise is the last category I'll talk about today, and this is the sound produced by turbulent jet flow with the ambient air. And every time that you see it or hear a jet take off, or you're flying on a jet, that's jet noise or jetting. And I'll be comparing that to what we get from volcanoes, because it turns out to be quite similar, actually. So volcanoes produce a lot of different types of sounds, and it's my job, or our job, to figure out what's going on and what's that say about the volcano. So here's just some of the examples that we get from volcanoes. The first one I'm showing on top, can you hear me okay? Okay. Is tremor that I mentioned. And this is a signal that's lasting for like 60 minutes, and it's continuous. We see hardly any changes in it. It's just kind of rumbling all along. The next bit here is these small explosions, and this was from this kind of background activity at Mount St. Helens. And these are, again, short duration, just little really gas puffs coming out, really low amplitude as well. The next, as we step up kind of like an energy and intensity level, we have these bigger explosions. So now we're going up, the value here, the pressure value is up to 40 pascals compared to like 0.04 before. So this is a larger eruption. But these are not distinct. We have mixing between the different types of eruptions. So we could have explosions and then tremor following right afterwards, and then explosions with jetting continuing on. And we'll see this for a variety of eruptions. We have a lot of different things going on at once. And the scales of these things are also quite amazing. You know, we have orders of magnitude differences in amplitude and duration. So this is a couple infrasound signals from these two big eruptions in Ecuador that I've studied in the past. And you know, it continued for like 12 hours long, producing this very strong sound that we recorded for hundreds of miles away from it. So how did volcano infrasound start? And really, how did infrasound in general start? And was really be traced back to the eruption of Krakatoa volcano in 1883. This is a huge volcanic eruption that occurred, and it had worldwide effects, both on the climate and scientifically as well. It also had produced very large tsunamis that killed tens of thousands of people. What's interesting for me, when we look back and study it, is the sound produced it. This is likely the loudest sound ever heard or recorded by humans. It was audible. People could hear it at 3,000 miles away. It was also recorded by barographs, which are just essentially measuring atmospheric pressure, like a weather sensor looking at atmospheric pressure changes. So these barographs recorded it worldwide. And it turns out that there was unexpectedly picked up at all these locations over the world. So this is Washington, Toronto, this is India, Australia, etc. And what's interesting with this as well is not only did it record it all around the world, but it traveled around the world 7 different times. It was so large. So this is a little animation of that pressure wave. It starts here at the source. It'll come back again, and then propagate out. So the red is as it's propagating out, and then the blue as the sound wave would be traveling back around the world. So this is unique. It doesn't happen, of course, very often, but it taught us people a lot about sound propagation in these very large signals. Infrasound research continued for a while, but it was kind of on the back burner. Like Doug said, it's a relatively new field. Well, it's not new, but it just hasn't been studied in great detail until somewhat recently, and that was due in large part to the advent of this global infrasound network. And the motivation and funding for this is from the CTBTO, which is the Comprehensive Test Ban Treaty Organization. And what they're interested in, this is a United Nations group, is to monitoring for clandestine nuclear tests. say some country wants to go test a nuclear explosion somewhere way out in the ocean, and they want to try to hide it. This network is set up to record signals from that, so they can't hide that. And so we're involved with the operation of some of these stations in the network. And we operate an array here in Fairbanks, as well as one in Washington State, Midway Island, which we just built. We have one in Palau, in Western Pacific, Diego Garcia, and then way down south in Antarctica, IS-55. This network, I want to point out, also records a lot of these large volcanic eruptions as well, so we can use that. So how do we record infrasound and process it? What do we do, and what have people really done in the past? Well, to kind of take a step back, how do we determine where sounds come from as humans? Well, we have 2 ears, and we use these ears and our brain to figure out what direction the sound is coming from. And we use often the differences in the travel time. So if a sound wave is coming at me this way, it hits one ear first and then the next ear. And so then I can kind of locate what direction that's coming from. Well, in the 1930s in particular, people were interested in where planes were coming from and maybe where explosions were. So they invented these funny-looking kind of artificial ears to try to locate where the signals are coming from with, I think, variable degrees of success. But what they do is have these kind of steerable antennas almost trying to locate where the sound came from. And it turns out that we do the same thing now, only in a little bit different manner. What we usually do nowadays is we take an infrasound sensor or microphone. This is Chaparral Physics. We produce these over at the Geophysical Institute. And we put it out in this kind of complicated setup here to reduce the noise. And then it'll be deployed out, and it'll record these changes in pressure, the sound wave. And it'll be one of a number of stations. So each of these gray stars here represents one of these, I guess, stations or elements that I would call them. And we put it out in a very specific configuration. So you could imagine each one of these is like one of your ears. Then we have a big explosion occurring somewhere, and this sound wave comes from the explosion. And as this sound wave comes across our array or our station, we do these sometimes fancy, sometimes straightforward processing techniques to determine what direction it's coming from and what velocity it's coming from. Because we want to know where the sound was produced. And this will come up later when we want to do that with volcanoes as well. What does this look like in practice? Here's an example, a picture from Witness by Antarctica, the array that we operate. So you can see here is this kind of pentagon. Each one of these little nodes here is where one of these pressure sensors is. This is on an ice sheet out here, and then there's 3 more here. So we have 8 sensors deployed. This is a distance of about 1.5 miles, I believe. Then it just happens to be that we have a source nearby. We have an active volcano, Mount Erebus, 26 kilometers away. And every time we get this little burp, little explosion from the volcano, it produces a sound wave. And this sound wave comes across and travels across our array. So we do that technique that I was talking about to see where the sound is coming from. This is kind of nice because it's a source that we can kind of test things on to make sure it's working right. But this is the essence of how we record things and process them. Without going into too much detail, we need to be concerned about how the sound propagates to our sensors. Because like I said, we can get these sounds thousands of miles away. But it doesn't just take a direct, easy path. And that's what a lot of our work goes in, is to this long-range sound propagation. And so at the ground, sound travels about 340 meters per second, or roughly 760 miles per hour. But as it goes up into the air, the sound is going to be affected by the wind and the temperature structure. And we have to be concerned about this all the way up, way high in the atmosphere. So this is the winds in the atmosphere for a certain time period, all the way up from 0 to 140 kilometers high. And then this is essentially the temperature or the sound speed. It's related. And then this is kind of the sound propagation modeling. But before I get to that, what's interesting to note when I look at the winds for this certain scenario is we have winds. What this is telling me, this little bump right here, is that the wind is blowing to the west at this altitude. So we have very strong winds, like 50 meters per second at 50 kilometers high, blowing to the west. And so I put that into my little propagation modeling, which I'm going to do here. So let's say I have a volcano or explosion right here. and I want to see how sound propagates to the west. As I do my modeling and taking into account the winds and temperature, it's going to tell me that this wind is going to affect the sound and it's going to refract it back down. So if I was right here, I would record the sound that took this path to it. And you can notice that it kind of takes this tortuous path sometimes. We have multiple propagation paths that can take. If I was to the east, the sound would take a much different propagation path. So you can imagine as we get further away, more complicated scenarios, this is how things start to look. Okay, so let's get to the fun stuff though, which is volcanic explosions and volcanoes in general. As I said earlier and showed some, there's a variety of different types of volcanic eruptions. Right here I'm just showing explosions. And this is kind of from smallest to bigger. And you can see the different types of signals that we get and then the different products from that. So here's this, notice the pressure amplitude for this little explosion right here is only 0.05 pascals, so relatively small. And then as we step up a couple levels here, now we're at 4 pascals. So a couple orders of magnitude higher in the pressure produced during this eruption. And if we look at the volcano, what we find is we have a little ash cloud going above it, maybe a kilometer above the volcano itself. When we start to step up even more, this is from Augustine volcano, which erupted explosively in 2006 in the Cook Inlet. We have a much higher signal. The amplitude for this one is like 100 pascals. And we recorded this, this one is at 3.2 kilometers, but we picked it up here in Fairbanks as well. And if you just happen to be looking around, at that time in 2006, you saw a very large ash cloud going way up into the atmosphere and causing a lot of problems for air travel, et cetera. So we can just look at the amplitude for this and we can get an idea of how big these explosions are. However, things like the Augustine eruption, they don't happen very often, and they're difficult to time and get right, or to be there when it happens. So what we try to do as scientists is we like to go to places where we know what's going to happen to kind of prepare ourselves for the more difficult scenarios. And a great place to do this was at Sakurajima volcano in Japan. We went there this summer. This is a very explosive volcano, and you get these very regular eruptions, maybe every hour or so. So the top I'm going to show here in this little video is the time-lapse data sped up 2 times normal, and the bottom is the infrasound. And I'll let this play a few times. So it's quiet, and then boom, we get an explosion. So you can see the ash cloud is starting to rise above the volcano here, and we also, if you can see it, there's all these volcanic bombs and ejecta flying away from the volcano. You'll see the flashes within the volcanic plume, which is really interesting. This is lightning in the volcanic plume itself. So again, we go to this volcano, we can go up short, and we can understand better the mechanics and how this type of explosion works. And then we can go to somewhere more difficult, like Cleveland volcano. This is probably the most active volcano we have in Alaska. It's also maybe the most difficult to access and to monitor. It's way out. Here's a map. Here's us in Fairbanks where our infrasound array is. It's about 1,800 kilometers or 1,100 miles out in the Aleutians. The nearest seismic station that we would use to monitor it is 75 kilometers away at the village of Nikolsky, which is difficult to get to in itself. So we don't have anything real-time or local to do. So what we tried to do, what I should say we've done over the past few years, is to use infrasound and take some of the things we learned from other volcanoes to help detect explosions and to monitor this volcano. It's often or usually monitored because there's no local network by remote sensing or by satellite data, which works well in some cases, but oftentimes we don't have the imagery that we would want or the satellite, or we don't have a good viewing because it's cloudy. So let's look at an example explosion. On December 29th in 2011, we picked up a nice explosion from Cleveland volcano onto our infrasound network. And what I'm showing here is about 2 minutes of data from our infrasound. And this is distance going away from the volcano from about 115 to 150 kilometers. And you can see these little short duration explosions that I talked about. And when we look at how fast that wave is going, it's about 335 meters per second, which is the speed of sound. So we know we have a sound wave going across our network here. So what we've done is we've set up a number of different detection algorithms to look for signals like these. And what happens for Cleveland in one of the cases is the infrasound is the only technology that actually picks up these explosions because of the style of them and where they are. In this case, we actually did get it with satellite remote sensing as well. So this is a satellite image. Here's Cleveland volcano. And there's this little blue kind of dot here, this small kind of detached ash cloud that's blowing away to the east. What's also interesting about Cleveland, because these are relatively high amplitude explosions, and because of the different properties of infrasound, is we're able to record these at very long distances as well. So we have an array that we operate in Dillingham in southwest Alaska, and then one in here in Fairbanks as well. And this is the infrasound data, the pressure data at Dillingham for this same explosion. So you can see it's quiet, and then we have our short duration, high amplitude explosion. And then we did some of those processing tools that I talked about before to look at the wave velocity. And it turns out that this signal right here has a velocity at like 0.34 kilometers per second, which is the speed of sound. So we know we have a sound wave moving across our array. We can also determine the direction or the azimuth of where the sound is coming from. And this dotted line here corresponds to Cleveland at about 230 degrees away. So we know there's this acoustic wave coming from the direction of Cleveland. So this gives us some more confidence of what is actually going on. The same thing could be said for our array in Fairbanks. So we picked up this little explosion right here, and we look at the velocity, and we know it's acoustic wave, and we look at the direction that it's coming from, tells us it's coming from the same direction as Cleveland. And so we set up all these different algorithms to detect eruptions like this. When this happens, it sends an automatic alert to someone at the Alaska Volcano Observatory, and then they can take the next steps to warn the aviation authorities, et cetera. So moving on to the next type of volcanic eruption, or the next type of sound from volcanic eruptions, is tremor. And for this, a great place to really study tremor is at Kilauea. And this is in Hawaii, where I used to do my work. And what's great about Kilauea is it basically never stops erupting. It produces continuous lava, gas, and infrasound at all times. So here's a map of kind of the volcanic region. This Pu'uo'o was the most active vent. It started in 1983 and continues to this day. And this is where all the lava was coming out, most of the gas, and the low-frequency sound as well. In 2008, things started to change. And over here, this other region, at the summit region, right where the visitor center is, gas started to come out of the ground, and people were kind of surprised by it. It turns out on March 19th of 2008, there was an explosion, and then this big vent opened up. So this kind of large hole, about 40 by 70 meters, opened up and produced a lot of sound, a lot of gas, etc. So what did the infrasound look like for this? Well, I'm showing a couple of things here. On the bottom, this is 4 hours of infrasound data, the pressure, and on the bottom, this is the spectrogram. And what this is I'm looking at the frequency on the y-axis here, and this is time. So I'm looking at how the frequency of our infrasound data changes over time. So you can see that this is quiet, this is essentially just nothing going on, and then boom, we have our explosion, this kind of opening of the vent, and then we have tremor, where the signal just continues on and on for hours. And essentially, since this started on March 19th of 2008, it's continued producing this sound until this day. So if you go look at this vent, and you watch what happened, this is in real time. For scale, this is about 40 meters in diameter. You can see that the gas is being pushed out of the vent and then sucked back in. Play it again. So as you see, it's being pushed out and then sucked back in. And this repeats itself over and over with a cycle of about 2 seconds. So this complete one full cycle, it's 2 seconds, or about 0.5 hertz. Now, when we look at the spectra, or the frequency of our infrasound data, we find something kind of interesting. We have this very dominant infrasound frequency at 0.5 hertz, or 2 seconds. This corresponds exactly with what we just saw in the video. So as this gas is being pushed out of the volcano and then sucked back in, it's producing a sound wave, and that's what we're recording. So what can we do with that, or what did we do with that? Well, we came up with a model to explain what's going on. And we tried to use this model to come up with an estimate of what it looks like underneath. So all we could see before was just at the top. You can't actually tell where the lava is, because at some point there's lava and a bunch of gas coming out, et cetera. And we want to know where that lava is. So here's a little cartoon drawing of the manifestation of that model. At some point, at depth, we have this magma and a lot of gas coming out. And then we have this big chamber underneath. And then above that, we have the atmosphere. And this is all we could see from above. And we came up with a model to explain this using Helmholtz resonance. And so you're probably familiar if you take like a bottle and you blow over the top of it, and you hear a single tone. And that's called Helmholtz resonance. And the same thing is happening here. And what Helmholtz resonance is this air gets pushed out and then sucked back in, out of this cavity and then sucked back in. This constriction, it has to have some sort of a neck, just like a bottle. Only this is a really big bottle. It's about 200 meters deep. There was another peak frequency in there as well, and this is due to like a standing acoustic wave occurring in there. So by using this model and these different frequency peaks, we came up with an estimate of how big this chamber is and where the lava level is. And then we could look at this and see how it changes as a function of time. So this is kind of a good idea to tell what's going on in the subsurface just from using the infrasound data. So the last type of infrasound from volcanoes that I'll talk about today is volcanic jetting. So first, let's talk about the sound from jet engines, or really what a jet is itself. So this is a little cartoon of what a jet engine, or what happens with a jet engine. So we have a nozzle here, and then we have air, turbulent air being pushed out at really high velocity. And what happens is you have different types of sound is kind of being emitted from this jet flow. This is what you hear every time a jet takes off or is flying by. We think what occurs at a volcano is very similar. So here's a picture of Mount Spur in 1992. Obviously, this is much larger than a jet engine. This is probably about a mile right here. And it's different composition. There's a lot of ash. But the same fundamental process is occurring. And so in a volcano, or when it erupts, we have these big eruptions. We kind of split it into a few different regions. So here's the volcano erupting like this. This bottom portion region is the jet. This is where momentum is driving this turbulent air or ash, et cetera, out of the volcano itself. Eventually, that loses its momentum and it kind of goes up and it spreads out. That's where you get the big umbrella clouds you might have seen from volcanoes. And so what we want to do, and what we've been working on the past few years, is comparing the infrasound from volcanic eruptions with the sound produced from jet engines. Because we know what happens in a jet engine and what the sound looks like very well, but we have a hard time understanding what's going on with these volcanic jets. One of the things we've done to do this is to look at the frequency spectra. Is what does the sound look like associated with these different types of eruptions? And it turns out for jet engines, always produce about the same type of sound, and you'll hear it in a minute. I'll play it. But if we look at the spectra, this is from a jet engine. It always has this same shape. And it turns out that our volcanic data has a very similar shape. So this is an eruption from Mount St. Helens in 2005 in black. We can compare it. It has a similar shape, which is kind of what we would expect to see. This is for Tungurahua volcano, a very large volcano in Ecuador. And comparing it to this to the jet noise spectra, it has a roughly similar shape as well. So what we think is this sound from these large sustained eruptions resembles the sound produced by jet engines. And in the next slide, I'll play the sounds, and you can hear it with your own ears. This is also important because every time we get this type of signal, we have a very hazardous eruption occurring, where there's a lot of ash coming out and it's being ejected to very high altitudes. So this is something that would be hazardous for planes flying by, etc. So now I'm going to play a video, and I guess it'll have the sound as well, of those two eruptions that I talked about. So to orient you, here's the infrasound, the pressure waveform, and this is the spectrogram. And it'll be sliding along. And as it plays, it's quiet, and then the eruption will start when the little red line goes over it. So try to play it again here. So just with your own ear, you can tell that it sounds kind of like a jet. It has a very distinctive sound in nature. Not a lot of things produce that type of sound. Oh, and I forgot to mention, so this is infrasound. You're not supposed to hear it, right? So I didn't play a trick on you. What I did is I took the infrasound data and I sped it up. I changed the sample rate of it basically and sped it up so we could hear it in the audible range. So I took the data, sped it up. For this one, it's 200 times. So that's normally not what it would sound like, but can just kind of shift it up so we can hear it. This next one is for Tungurahua volcano. So this is a larger eruption occurring over a longer time period. This is 6 hours of data that I'm going to play for you. So again, here's our pressure waveform, and here's the eruption itself. And you'll hear the jetting, but you also hear these little short duration kind of pops. And each one of those pops is really a big explosion occurring as well. So as you can tell, it sounds a lot like a jet engine. One of the things to note too is here's a picture of what was occurring during this eruption. I want to note that this was a big eruption, produced ash all the way up to 50,000 feet. So this is something that obviously we need to be aware of, and we'd like to be able to not necessarily predict, but when it's occurring, identify that this type of eruption is happening. The last type of kind of jetting that we've looked at, and actually before I get there, I want to set you up. If we look at our pressure data, so here's 0, and I want to look at the amount of positive pressure pulses versus the amount of negative pressure pulses. So if I have 0, I can see that my data is kind of evenly distributed. It's kind of symmetric in the amount of positive versus the amount of negative. Well, there was an eruption in East Africa in 2011 from Nabro volcano. This is from a satellite image of this eruption. And it turns out that this volcano had a very interesting and particular type of sound produced. So here's 1 minute of data from Nabro in blue, and here's 0. And you can see rather than being kind of evenly distributed, there's a lot more positive values than negative. And that's what I'm trying to show over here without going into a lot of detail. And also, the other really notable feature about this are this really sharp rises in the pressure waveforms. This is different than what we've seen at other volcanoes, but maybe not what would be unexpected. So when we compare this, our data from Nabro, with a jet engine from a supersonic jet engine test. This is an F-18 at afterburner, so very high velocity. We have sound coming out at hundreds of meters per second. Turns out that the sound looks and sounds a lot like what we get from the volcano itself. And actually what it's most similar to is to these really large, hot, high-velocity rocket engines. So if you want to launch a satellite up into space, you use one of these big GEM 60 rockets. And turns out that the sound from these rockets looks a lot like and sounds a lot like what we record from the volcano. And this is like a couple of meters in diameter. It's very hot, very high velocity. So now I'm going to play the sounds for these three, and you'll hear this kind of unique features to this, and it kind of sounds like crackling or popping. So this is Nabro sped up a couple hundred times. Okay, so that ripping that we hear, the kind of crackling or ripping sound is these really sharp compressions that we get. So now I'll play the F18 data. So the frequency was a little bit different, but this crackling sound is similar still. And then the last one. So if you were to go to, I guess it used to be this, oops, not supposed to go there yet. If you were to go watch the space shuttle take off, or I guess when it did take off, or watch a satellite being launched, that's what it would sound like, this really crackling sound. And what's occurring there, what we think is happening, is when you have this jet, you have these shock waves coming off of the jet here. And that's what's producing each one of these little compressions is a shock wave coming out of this. And although we weren't able to observe and view the Nabro eruption, I think we've seen something similar. So this was a video taken from the Mount Spur eruption in 1992. So just for scale, this is probably, I don't know, a few hundred meters. And if you look at the base of the volcanic jet, you can see these visible shock waves emanating from the jet itself. I think they'll zoom in here in a second. Yeah, so on the left side, you can see these shock waves coming out. So I think the same thing that's happening there is what was happening at Nabro and what's happened at, with these other jet engines as well, the supersonic ones. So kind of to leave you what we're working on now and some of the future work, and this is at Krymsky Volcano in Kamchatka, Russia, is I've talked about the different types of infrasound that we get from volcanoes. Well, we want to take the next step and say, okay, well, we get this type of infrasound, now what's actually coming out of the volcano? And come up with really kind of quantitative estimates of how much ash is coming out, how much gas there is, because this is what's really important for a hazard. Is what type of emissions and how high, how much of them. So we've gone through a few different types of eruptions that we've seen at this volcano and looked at this specific infrasound. And now we want to compare that to how much gas is coming out. So this is kind of a running loop of SO2, sulfur dioxide, and how much is coming from the volcano. And we see different amounts of SO2 coming out for these different types of eruptions. Okay, just to kind of summarize what I've talked about today, I think I've shown you that active volcanoes produce a lot of infrasound, a lot of different types of infrasound, and each one of these volcanoes has its own kind of unique signature. And so what we try to do is understand that signature and then figure out what we can say about the volcano, both to help understand what's going on and then eventually monitor it. And this is particularly useful, I think, in a place like Alaska, where a lot of our volcanoes are difficult to monitor and understand what's going on. Thanks.